Hello, good morning. Here yet again for another session of CENG 4412 Steel and Concrete Design. So today we're going to continue on looking at some elements of and aspects of beam design and beam calculation, steel beam design in particular. So the first thing I want to talk about is a continuation of local buckling, or just discussing a few other aspects here. So let's look at local buckling. I have discussed this previously, but I want to discuss it at a bit more rigorously. So local buckling, what is local buckling? Local buckling, well, local buckling again. Local buckling is fundamentally, in terms of the AISC steel manual, we use local buckling to determine which section in Chapter F to use. This is how we determine which section in Chapter F to use. Which section in Chapter F to use. So let's talk about this. Let's talk about the theory of this. Now, fundamentally, rolled shapes, all sort of steel shapes, can be thought of as being made up of plates. So consider a wide flange shape here. Consider a wide flange shape. Just a generic wide flange shape. And let's say that let's consider 3 plates here. Well, or at least 3. We could consider the whole flange as a plate. But in particular, as we discussed previously, when I'm talking about compactness, I'm talking about just one cantilever plate here for the flange. So maybe this would be one plate here. The web could be another plate here. And then this flange could be another plate. So 2, 3, that kind of thing. So fundamentally, structural shapes are made up of plates. Structural shapes are made of plates. Even though they're not usually really welded together plates, even though they're rolled, they can be thought of as plates, are made of plates. And these individual plates can buckle before the overall shape will fail. Or in other words, if one plate buckles before the entire cross-section, plate buckles before the entire cross-section fails, entire cross-section reaches intended stress, or reaches a stress limit. Before the entire cross-section reaches the intended stress limit, then it never does. Then it fails prematurely. So in other words, even though this is a local phenomenon, it does reduce overall capacity. So, or we can simply say, let me put this in red just for extra clarity, that even though this is a local phenomenon, or this local buckling reduces overall global capacity. Reduces global capacity. So local buckling does reduce overall global capacity. That's the key takeaway here. So basically, even though so when I say global capacity, we're talking about the type of global capacity that we would predict that we would have in terms of pure, mechanics of materials type beam design theory, in terms of global lateral torsional buckling theory, that kind of thing. So long before you get to that upper stress limit, you can have a failure due to local buckling. And the way the code handles that is first we have certain limit states, and we've already learned how to check these briefly. Your BF over 2TF, that sort of thing. We'll check individual elements of a section to see if that will ever control will ever control overall capacity of the section, and then based on that, we'll choose which section in Chapter F that we are in. So let's talk about stiffened versus unstiffened elements next. So stiffened versus unstiffened elements. So I want to talk about stiffened versus unstiffened elements. Yes, local buckling reduces global capacity. Okay, so stiffened versus unstiffened elements, and I will throw these slides on the course Canvas page. So stiffened versus unstiffened elements. So in terms of cross-section, what do we mean by stiffened versus unstiffened elements? Well, let me draw two wide flanges again. Two generic wide flanges. One here and one here. You hear this phrase, stiffened versus unstiffened. So let's look at how flanges versus web plates behave when subjected to buckling. So if I have a web here, if this thing's going to buckle, it has to buckle out like this. The web will have to buckle out something like this. It will be buckling at both ends. So, but it is supported. It's going to buckle out at the middle, but it's still supported at both ends. Meanwhile, though, if the flange is going to buckle, it's basically sort of like a cantilever. It's going to be able to buckle out like this. It's going to buckle out like this. So when I say a stiffened element, I mean an element within a cross-section that is braced on both ends, while an unstiffened element is one that is braced only at one end. So stiffened would be an element in a cross-section. That basically means an element in a cross-section that is braced at both ends. Braced at both ends. And unstiffened cross-sectional elements just braced at only one end. Braced at only one end. So something like the web here, this is what we would classify as a stiffened element. And this here we would classify as unstiffened. As unstiffened. Okay, and also another key thing to keep in mind is that unstiffened elements by their nature are more likely to have local buckling. Again, because they're braced only at one end. More likely to have local buckling. Local buckling. Oh, sorry about that. Now, it is not impossible to have buckling in the web control, but if you can think about this, we know that flanges are going to more easily buckle than webs. So the only time that the web buckling would control is typically on members with very, very slender webs. So that's usually not ever going to happen. There may be some cases where it would happen, but in almost any rolled shape, that's not going to occur. But if you had some very tall built-up member, like a really tall box beam, a really tall railroad bridge, railroad beam, that kind of thing, railroad bridge beam, that sort of thing, in that sort of case where you were literally building up a very tall web out of plate, in that particular case, web buckling can actually control. But anyway, so let's look at again at a let's look at a review of how to calculate this. So checking for local buckling, let's look at the code approach. Local buckling, code of check. And we've already discussed this a bit, but I want to review again. So local buckling code checks. Again, this is going to be table, let's see. This is found in table B 4.1b. Table B 4.1b, starting on page 16.1-17. And there'll be a whole bunch of different formulas for different types of elements. So basically, local buckling, LB, is checked using limiting width to thickness ratios, using what are known as limiting width to thickness ratios. Width to thickness ratios. Using limiting width to thickness ratios. So, for example, let's look at a W section. And we looked at flanges before, but I also want to show you that we can also there are also limiting width to thickness ratios for the web. So if I want to draw out a generic W section here, and I'll label the important dimensions. So if I have a generic W section, like this, and like this, the relevant dimensions are going to be like this. And let's see here. So first of all, I have my H for my web. My dimension, my relevant dimensions are H, the distance between the flanges. This is H, and H would be equal to D minus 2T, or 2 times the thickness of the flange. So again, H would be equal to D minus 2 times the thickness of the flange. And then I also have my thickness of my web here, TW. And then I also have my, so that's my limiting, that's the width of my limiting element, and this is my length of my critical element there. And then when I'm checking the flange plate, so again, when I'm checking the web plate, this is gonna be my plate width, and this is gonna be my plate length. And then when checking the, I should say this is gonna be my plate thickness, and this is gonna be my plate length. And then when checking the flange plate, this is gonna be my plate length, and this is gonna be my plate thickness. So this is my thickness of the flange, TF, and the crucial dimension here is BF over 2. BF divided by 2. And so then the limiting ratios here are as follows. If I want to know whether a web is going to be slender, compact, etc., the limiting ratio is H over TW. The height of the web divided by the thickness of the web. For flanges, if I want to know whether a particular flange is compact or not, the ratio I'm going to use is simply BF over 2TF, as we've discussed previously. Over 2TF and again, these are our limiting ratios. These are our limiting ratios, and we'll compare these, and we'll compare to what I'm going to call lambda P and lambda R. Lambda P and lambda R. Lambda P and lambda R. Okay, and these are the slenderness limitations that are found in the in that table. So basically, we'll just that's the 0.38 square root e over fy, square root e over fy, that sort of thing. And then we also have for each different type of shape, there'll be a different form of slenderness limitation. So for example, if we were dealing with an angle, an L shape, we would have something like this. We don't have when we're dealing with angles, we don't really have flanges and webs. Rather, we just have two legs. So I would just be using, say, a B and a T. B and T here, where B would be the width of my leg, and T would be the thickness of that leg. And T here. And so legs then, legs have a limiting ratio of simply B over T. Or, simply B over T. And we could talk more, we could list all the rest, etc., but we could stay at this for quite a while, but the point is there are many others, for C channels, C shapes, all sorts of things, etc., etc., T shapes, etc. But the key is that each shape will have its own ratios. Will have its own critical ratios. Okay, so once we have these, of course, what do we do with them? Well, we compare them again to our lambda p, lambda r, etc. So once we have limiting length to thickness ratios, once we have limiting or our width to thickness ratios, we'll compare it to our lambda p and lambda r. Lambda p and lambda r. Okay, so again, we have, as we discussed previously, we're going to have a few zones here. We have our lambda p and our lambda r. And anything less than lambda p, we just refer to our, basically, on this axis, we would plot our, on this axis, we're basically plotting our ratio here. So this is our, basically our, a number line with our ratio, with the thickness ratio. And then anything less than lambda p is going to be compact. Between lambda p and lambda r, we'll refer to it as non-compact. And anything more than lambda r, we'll refer to as slender. And we don't just refer to the entire shape as that. Rather, we'll say that, this element has a slender web, or this element has a non-compact flange, something like that. Okay. And so that's the basic idea there. And then, so again, we find our we find our width to thickness ratios, and then we'll use whatever numbers we have to use for lambda p, lambda r. So for example, you might have lambda p, for example, for certain types of shapes, as we discussed previously. If we have flanges of rolled I-shaped sections, channels, and T's, lambda p, for example, is 0.38 square root of e over fy. You may remember that from previously. So flanges of rolled I-shaped sections and T's in flexure, that sort of thing. And then lambda r is 1.0 times the square root of e over fy. So, for example, these are the lambda values that you would use if you're dealing with, say, W sections in flexure. And then you just you look at your number and you look at your limiting length to thickness ratios for your flanges and say, okay, well, if it's less than this number, if it's less than lambda p, I have a compact flange. If it's between here, I have a non-compact flange. And if it's greater than lambda r, I have a slender flange. But what do you do with this once you have it? Once you know whether you're compact, non-compact, etc. Once you know if your sections web and flange are compact, then you will simply go to the appropriate section in the code. In the AISC code. AISC manual. So for example, and it will depend on what type of shape you have, but for example, if you are dealing with doubly symmetric eye shapes, for doubly symmetric eye shapes, we'll use F2. We're going to talk primarily in this class about section F2, really because that's the simplest one. And this is kind of a survey course of steel and concrete design. F2 is going to be for you'll be using if you have both a compact flange and a compact web. Compact flange and web. F3 would be for compact webs, but non-compact flange. And F5 would be for a slender web. These are just a few. And there are other sections in Chapter F as well that you might look at. Okay, so let's see here. Now, let's see. Then I have one other thing I want to talk about in this portion of the lecture, and that is CB. We've mentioned this previously, but I do want to discuss it now. Although maybe I'll include this as a very short part 2 here. All right, I think I'll stop this here, and we'll continue right now.